Hey, hello and welcome back, everybody. This is the worked example section for the second order linear homogeneous constant coefficient ODEs. And we're going to start out with a slightly stronger theorem. So we'll say a stronger solution theorem. Stronger in the sense that we're going to incorporate Euler's formula into our solutions. So I'll just write this out again. The solution to the second order ODE being everything in the title, a y double prime plus b y prime plus cy equals 0 is given by y, we'll say of x, even though this could be x or t, so it could be t. It's given by c1 e to the first eigenvalue, so negative b, plus the square root of b squared minus 4ac, all over 2a x plus c2 e to the negative b minus the square root b squared minus 4ac, all over 2a x. This is going to be true when b squared is strictly greater than 4ac. Strictly greater is going to guarantee that this is a square root of a positive number, and therefore you won't have any imaginary terms there. So you have the advantage of leaving everything as an exponential. We can write it as c1 e to the negative b divided by 2a x plus c2 x e to the negative b divided by 2a x when b squared equals 4ac. And this is, of course, just because when b squared is equal to 4ac, these terms are going to drop out, right? So these terms become 0 when they're equal to each other, so we just have the negative b over 2a. But the price of repeated roots, if you go way, way back to when we had a non-diagonalizable matrix, it gave us an extra term of whatever was sitting up top out front. And so the case of repeated roots is giving us an extra term of x. And then the final case is going to be c1. It's going to be c1e to the negative b over 2a x. So that's just like the term above. Then we're going to get a cosine of really the square root b squared minus 4ac over 2a terms. But because this is going to be the case when b squared is less than 4ac, we're going to swap the order and we're going to write it as 4ac minus b squared all over 2a. That's multiplying x in the cosine, and similarly for sine. So we'll get a c2 e to the negative b over 2a x, and then we'll get sine root 4ac minus b squared all over 2a x. There's a c here as well. So that's going to be kind of the more general setting where I've just gone ahead and used Euler's formula to give you the very last situation where we have a cosine and sine, and because b squared is less than 4ac, I've swapped the order in the square root to make sure everything looks good. So this is a pretty nice situation. I'll go ahead and mention that each of these x's, the x's could always be t. Like that. Could be t instead of x, right? That's for the same reason. We're just looking at whatever our independent variable is what's going to go there. But that is our solution. So we'll go ahead and square this off as a nice, particularly strong theorem that we can rely on to basically solve any ODE of this form, depending on the sign of b squared minus 40c. And this will set us up really good to finish some problems for today. So we're going through our worked examples. Let's take the first one, for example. Let's solve the ODE given by y double prime minus 2y plus 2y prime plus y equals 0. We'll say y and 0 is equal to 1. Y prime and 0 is equal to 1. So our solution is going to be one of the three forms. Up above, we just need to check. So in step one, we'll go ahead and check b squared, which happens to be negative 2. So that's negative 2 squared, which is 4. And we'll check that against 4ac, which is 4 times 1 times 1, which is going to be 4. And what do you know? They're the same, which means we're looking at the middle case. When b squared and 4ac are the same, we're looking at the middle case. So that's going to tell us that our solution, and I'm going to use t here, okay? So one reason why I'm using t, note that the inputs here, 0 and 0, are the same number, which makes this an initial value problem. An initial value problem evolves over time. So that's usually the way that I decide if I'm using t or x. It's really not a big deal. I mean, you're going to get the problem right, but you'll just have a better understanding of what it's saying if you go ahead and use the right variable. So our solution is going to be the middle line with t as our variable, and let's recall that b is negative 2, a is 1, and c is 1. So that when I write my middle line out and I write e to the negative b, so that's negative 2 over 2a is 2 times 1 against t plus c2 e, well, there's a t here, right? c2t e to the negative 2 divided by 2 times 1 against t. I can simplify this and I get c1 e to, that's positive 2 over 2, so just t plus c2 t e to the t. That's going to be my solution, barring some choice of constants. I mean, I still have to find these constants, and I need to use conditions to find these constants. What are my conditions? They're these two values. So the conditions are y0 equals 1, y prime at 0 equals 1. To go ahead and use those, I actually have to evaluate at 0. So I'm going to go ahead and plug the 0 into my solution that I've just developed. If I plug 0 in, I get c1 e to the 0 plus c2 times 0 times e to the 0. That's just giving me c1 because e to the 0 is a 1. There's 0 times a 1. Importantly, there's a 0 up front. So I have c1 equals the right-hand side of my condition, 1. So that made my life pretty easy with regards to c1. I'm still missing c2. So when I have this y prime at 0 equals 1, I need to calculate y prime first. So must calculate the derivative in time, then evaluate at 0. Because if I evaluate at 0 first and then take a derivative in time, I've evaluated myself into a constant, and then the time derivative will always be 0. That's not going to give me any information. So I need to take the time derivative first and then evaluate 0. So I'm going to take a time derivative of this object. And thankfully, the time derivative of an exponential is fairly easy. That's itself. So I have c1 e to the t, but there is going to be a product rule. Product rule when I take a derivative. So the product rule there is going to make my life a little trickier. I have c2, derivative of the first term, derivative of t is 1. That's why I have e to the t. Plus c2, what is the derivative of the second term? That's e to the t. The derivative is also e to the t. And so I'm left with this after my product rule. And at this point, I say then evaluate it at 0. So I can go ahead and plug in t equals 0 here. That's going to send me to y prime at 0 is equal to just plugging in 0, 0, 0, 0. It's going to give me c1 plus c2 plus 0 because c2 times 0 times 1. So I have those two numbers. This has to be equal to the right-hand side here. So this is equal to 1. I also know from my earlier example, c1 is equal to 1, so this is actually 1 plus c2 equals 1, or in other words, c2 is 0, and my solution becomes about the easiest thing you could expect. Let's go back to the beginning, but let's actually plug c1 and c2 in. Going back to the beginning, that's here, so c1 was equal to 1, c2 is equal to 0. Plug those in, and I'm left with 1 copy of e to the t, and I'm left with 0 copies of what's left. So I can just get rid of the 0 of what's left. My solution is given by e to the t. Let's go ahead and verify this. It's not going to be too bad to go ahead and verify. So let's recall the ODE was y double prime minus 2y prime plus y equals 0. We recall it said that y at times 0 was 1, and y prime at times 0 was 1. So to verify, we need to check 3 equalities. And to do that, we're just going to compute the left-hand side. So computing two derivatives of y, I'm going to do two derivatives of e to the t. Well, y is e to the t. That means y prime is the derivative, which is also e to the t. That means y double prime is two derivatives, which is also e to the t. So y double prime is two derivatives, e to the t. I'm just going to plug each of those three terms in. And what I'm left with is e to the t minus two copies of e to the t plus e to the t. What happens when I go ahead and add these all together? Well, I have two negatives, two positives. This is equal to 0. What did I want it to be equal to? 0. So there, I've checked the first equality. I can check the second equality just by plugging a 0 in. Y at 0 is e to the 0, which is 1. Easy enough. Y prime at 0. Here's y prime. That's going to be e to the 0 as well, also known as 1. So we've checked that. So there you go. We've checked all three equalities and we are verified. This one's very easy to verify. That's nice. Let's go through another example. Let's solve a boundary value problem now. So let's do y double prime minus 4y prime plus 3y is equal to 0. Let's go ahead and solve it against the boundaries. Y at -1 is 4, and y at 1 is -4. First thing we need to do in every case is check b squared, which in this case b is -4. That's going to be -4 squared is 16 against 4ac. 4ac will be 4 times 1 times 3, which will give me 12. And we find out that b squared, 16, is greater than 4ac, which was 12. B squared greater than 4ac, let's go up to the beginning. Looks like we are in the top case, which is when everything is fairly straightforward. I don't have cosines or sines or repeated roots. And so my solution is given by y, and I'm writing it as y of x now. Why am I choosing x? Because these two values, two different inputs, so a boundary value problem, and so I'll make my independent variable x. So I'll choose x as my independent variable because it's a boundary value problem. And then we write this as c1 e to the -b plus the square root of b squared minus 4ac all over 2a on x plus c2 e to the -b minus the square root b squared minus 4ac all over 2a on x. And I can go ahead and actually evaluate, right, because b is -4, a is 1, and c is 3. If I evaluate these exponents, I have -4, also known as 4, plus the square root of 16 minus 12. I already calculated those earlier. I'll divide it by 2. X plus c2 e to the 4 minus the square root of 16 minus 12, all divided by 2 against x. And if I simplify those terms, what is 16 minus 12? That's 4. I'm taking the square root of 4. That's going to be 2, right? So I'm looking at 4 plus 2, also known as 6, divided by 2, also known as 3x, plus c2 e to the 4 minus the square root of 4 is 4 minus 2, also known as 2, divided by 2 is 1 copy of x. So my solution takes this form. Now I just need to make sure I can meet the boundary conditions. So step 3, meet boundary conditions, or other conditions if it's an initial value problem, with C1 and C2. So here are boundary conditions. If I go back to the top, where that y at -1 was 4, and y at 1 was -4. So it's time for us to get good at calculating, solving systems of equations. Let's go ahead and evaluate the first case. Y at -1. I'm just evaluating, my solution. I'm claiming at -1. C1 e to the -3 plus C2 e to the -1. I'm putting a -1 in for both cases of x. What does this have to be equal to? Well, it has to be equal to 4. Similarly, y at +1, I'm just evaluating both x's at a +1, and I get C1 e cubed plus C2 e to the first power is equal to -4, because that's the right-hand side of my second equation. So now what I have here is a system of two equations and two unknowns, and we just have to get good at solving them. That is why everybody took Algebra 2 before they took this course. So let's go ahead and solve the system. for C1 and C2. The easiest way to do that is by substitution. So I'm going to solve the first for C1, which means I'm dividing by e to the negative 3, or I could multiply by e cubed. Let's go ahead and multiply everything by e cubed because of my exponent rules. So that's going to leave me with C1, and then e cubed and e to the minus 3 will cancel each other, plus C2, e cubed against e to the negative 1. So there's a power of 3 and then a power of negative 1. 3 minus 1 is 2, equals 4 e cubed. And then if I subtract C2 e squared, I get C1 is 4 e cubed minus C2 e squared. And now that I've solved for C1, I can plug that in for C1, leaving me with 4 e cubed minus C2 e squared against e cubed plus C2e equals negative 4. What do? I need to solve this for C2. I might as well distribute this e cubed. My exponent rules are going to give me 4 e to the 6th because of 3 plus 3, minus C2 e to the 5th because of 2 plus 3, plus C2e equals negative 4. I can go ahead and pull 4 e to the 6th to the right-hand side, giving me, and then factor out C2, giving me negative e to the 5th plus e equals negative 4 minus 4 e to the 6th. Divide everything by e to the 5th plus e, leaving me with C2 is, well, let's factor out a negative 4. Negative 4 factors out. The numerator is 1 plus e to the 6th. Denominator is really e minus e to the 5th. And that's all that C2 can be. I mean, these problems are ugly. That's our life sometimes. That's what C2 is. We'll go ahead and grab it, plug it in up here for C2, giving me a value of C1 as 4 e cubed minus negative 4, so we'll just say plus 4, and then C2 is 1 plus e to the 6th, e minus e to the 5th, e squared. So there's C1 and C2. I'm really not going to simplify those any farther. There's no point. You could plug it into a computer and get a numerical answer for both of them. Then you'd have kind of a numerical approximation to your solution. But we need to finish off by actually evaluating our solution on C1 and C2. So we have that y of x is C1, 4e cubed plus 4, 1 plus e to the 6th over e minus e to the 5th, e squared against e to the 3x, and then we're going to add C2, which is here, negative 4, 1 plus e to the 6th over e minus e to the 5th. And then we'll write this against e to the x, and then we'll simplify my terms a little bit. So it's really minus 4. I don't need those parentheses. Minus 4. So that is our solution to this ODE. Like I said, you can evaluate those numerically if you like a few decimal places better than an exact answer. Let's accomplish one final second order ODE. Let's solve y double prime plus 4y equals 0. Let's say y at 0 is 1 and y at pi over 2 is 1. Now the pi over 2 is making me suspicious that this is radians, and so we may have sine and cosine in our solution. It's kind of like the mathematically mature thing to recognize is that radians tend to show up when we have sines and cosines. Let's go ahead and do our first case and check b squared, which in this case unfortunately is 0. B would be the term, right? There's really a plus 0 y prime here. So b is 0, b squared is 0 against 4ac. That's 4 times 1 times 4. It's going to be 16. 16 is bigger than 0, so we have that b squared is less than 4ac. B squared less than 4ac. Go to the top, we're looking at the very last situation here. So yeah, we will have sines and cosines. That means our solution is given by, let's write this out again, a is 1, b is 0, c is 4. Our solution is given by y, well, should I use x or t? Are these numbers the same or different? These numbers are different. So use x, my spatial variable, because it's a boundary value problem. So my solution will be y of x, c1 e to the negative b over 2a x cosine root 4ac minus b squared all over 2a x plus c2 e to the negative b over 2a x sine root 4ac minus b squared over 2a x. And then let's actually plug in a, b, c. Since b is 0, that's a 0, that's a 0, that's a 0, that's a 0. And so my exponentials are e to the 0 power. The exponentials both turn into 1, and I can forget about them. What I'm going to be left with, especially when a is equal to 1, I basically have the square root of 4ac over 2a. So, and a is 1. So this is really the square root of 4c over 2. Square root of 4 times 4, square root of 16 is 4. 4 divided by 2 is 2. Cosine 2x plus c2 sine 2x. So now in step 3, we need to solve for c1 and c2. With my boundary conditions, which in this case, at 0, I need to be equal to 1, and at pi over 2, I need to be equal to 1. Let's go ahead and plug those numbers in. If I plug 0 in, I get y of 0 is going to be c1 cosine of 0 plus c2 sine of 0. Everybody's favorite unit circle's back. Here's 0 radians. The point at this point is 1 comma 0. So cosine of 0 is 1, sine of 0 is 0. And what do we have? We have cosine of 0 is 1. c1 times 1 plus c2 times 0, because sine of 0 is 0. So we're just left with c1. c1 has to be equal to the right-hand side, 1. We now try y at pi over 2. This is going to be c1 cosine of 2 copies of pi over 2. So cosine 2 copies of pi over 2 is pi, plus c2 sine of 2 copies of pi over 2 is pi, whereas pi radians, all the way around, pi radians. And what is our point there? Our point there is negative 1 comma 0. Cosine of pi is negative 1. Sine of pi is 0. So I end up with negative 1 copies of c1, also known as negative c1. 0 copies of c2, also known as 0. I have that c1 has to be equal to the right-hand side, 1. Let's examine these two identities. c1 is 1 and negative 1 at the same time. This is a big old problem. And we run into the first case in everybody's career. This is an important thing to note about boundary value problems. There is no solution to this ODE. Because this resulted in a contradiction, there's no solution. And that is a perfectly valid answer. We can construct mathematical problems without solutions all the time. This shouldn't be too terribly surprising. We're doing everything in our heads. They may not represent a physical reality because we've just constructed this with objects from our head. And in the event they don't really reflect a physical reality, sometimes they still have solutions. We have hypothetical solutions to hypothetical problems. But there are certainly cases where we just don't have a solution, and we all have to be okay with that. Anyway, I'm going to stop there, leave you on a bright note. See you in the next video.